So as we're nearing the end of our series on elementary group theory, we're going to talk about generators and relations today. So free products, free groups, and all that jazz, and it's really going to get quite big picture. We're setting the stage this time so that we can talk about in the final video, which is going to be the next one, the relationship between algebra and geometry and how groups fit into the center of that picture. And when we're talking about generators and relations, we're really talking about the algebra side of that relationship. And we're talking about, what if we just define, a squared b is equal to the identity, or perhaps AB, A inverse b is equal to a squared. Can we define a group just by saying that its generators, or certain elements in the group from which we can obtain other elements, satisfy some equation, some relation defined by this algebraic equation? And the answer is going to be yes. And what we're going to call this is a presentation of the group in terms of generators and relations. And we will get to that in more detail in just a moment. All right, so we're going to jump right into it here with the definition of a free group. So, pick a set X and a set X inverse such that these two sets have the same size and that they are disjoint. So we have X intersect X inverse is the empty set, and the cardinality of X is equal to the cardinality of X inverse. And of course, the second statement is equivalent to defining a bijection, let's call it alpha, between them, right? So we have some bijection, and for any element in capital X, we'll call it little x, denote the image under this bijection, could be any bijection we pick, we will simply call little x inverse. Now we're going to pick a third set with one element in it, a singleton if you will, which we will label 1, but it doesn't matter what is in there, so long as it is disjoint, once again, from the union of X and X inverse. So we pick a third set here, which is a singleton. All right, now that we have these three sets, we are going to define a word on X. A word is simply going to be an infinite sequence of elements A1, A2, A3, etc., such that each A sub I is somewhere in here, is in the union of those three sets we constructed up here, and such that there exists some K for which A sub n is equal to 1 for all n greater than or equal to k. In other words, the word terminates. So we're only considering finite words, and in fact we will often write these words simply as A1, A2, A3, all the way up to A sub k minus 1. Right? Because everything after this is just going to be 1, 1, 1, 1, and we're not going to care too much about that. Furthermore, we're going to define a reduced word to be any word such that A sub I plus 1 is not equal to A sub I inverse. In other words, is not equal to alpha of A sub I, right? So we do not have inverses sitting next to each other in this sequence. And also we're going to have that if A sub I is equal to 1, then this implies that A sub j is equal to 1 for all j greater than or equal to I. In other words, the first one you see, so with any word we could have, A sub, well, here, we could have x1, x inverse, 1, 1, 1, and our sequence of ones begins. But in a reduced word, If we have this 1, then that means everything after it is going to be a 1. One more definition here. We are going to define the empty word to simply be the sequence 1, 1, 1, etc. Now each reduced word on x is going to look like this, right? It's going to be x1 to the plus or minus 1, x2 to the plus or minus 1, where x1, say, or x sub I to the positive 1, we're just defining to mean the usual x sub I, and of course x sub I to the negative 1 is equal to the inverse element under our bijection. So each reduced word is going to look like this, dot dot dot, all the way up to, say, x sub n to the plus or minus 1, and then 1, 1, 1, off to infinity. And as I alluded to before, we're going to write this as x1 to the plus or minus 1, x2 plus or minus 1, all the way up to xn plus or minus 1, and leave off the infinite chain of 1s. And now we get something that looks vaguely like a word, right? We just have a set element followed by a set element, right? All these are in x now, writing it in terms of the elements in x. And if we have two adjacent elements which are in fact the same element, say x1 is equal to x2, then we could instead write, say, pretend our sequence is x1, x2, x3, no inverses, say. Then we could write this as x1 squared, x3, etc. So this is how we're going to write our reduced words. Now we're going to define the product of two words in the following way. Suppose we have x1 to the alpha 1 all the way up to xm to the alpha m. This word times y1 to the beta 1 all the way up to y sub n to the beta sub n, where x sub I and y sub I are in the in the set x for all I. Well, we're just going to define the product via concatenation and reduction. So what do I mean by that? I mean, we are defining the product of these two words as the reduced form of this. Why do I say the reduced form? Well, we need that reduction step in case x sub m to the alpha m is equal to y1 to the beta 1 inverse, right? And we have to allow this to happen actually a finite number of times, because say this pair cancels, and then the adjacent pair cancels, and then the adjacent pair cancels. And I'm not going to get into the details because it's really a mess to describe something which is fairly obvious. But what's going to happen is eventually one of these is shorter than the other, so either one of them will completely run out and you'll be left with part of this word or part of this word and a bunch of ones, and part of the reduction process is taking out the ones, right? Or you're going to reach a point where they're no longer inverses, these pairwise elements. So basically what we're going to have is the concatenation of two words plus any necessary reductions as a result of putting adjacent elements together that could be inverses. And that's going to be how we define the product of two words. Importantly, the termination of this reduction process tells us that the product of two words, rather two reduced words, is again going to be a reduced word, which means we have just demonstrated closure. Or if you want to go to a little bit greater length, you can more rigorously demonstrate closure. But you see that with the pairwise canceling and replacing with a 1 and then removing the 1 and doing it iteratively, we are going to get a reduced word, and thus we're going to have closure under multiplication of words. Alright, first theorem. If x is a non-empty set and f of x is a set of all reduced words on x, then under the defined operation, f is a group and f is generated by x. If x is the empty set, then f of x is the trivial group. And this group f we call the free group on the set X. Has a special name. Also, you may want to recall that generating a group using a set means that if you take all groups which contain the set X, so let's say the family f sub I, indexed by some indexing set, some family of groups such that each fi contains X, and you take the intersection of all of these f sub i's, this is going to give you the set generated by X. And all it's saying is that the whole group, the free group on X, is generated by the inclusion of X in the free group, essentially. So this is a good point to make now, is that X in this context is different from X in that context, right? In this context, X is just a set. Whereas when we talk about X in f of X, we are talking about the inclusion iota of X. I'll use iota today to denote the inclusion map, which is actually in the free group, right? So the only difference is that this X has a group structure, or is part of a greater group structure, whereas this X was just a set. So if we draw a diagram, we have X being taken to f of X by the inclusion map, and this is something that we will use frequently. Now, I'm not actually going to prove this, because by now, if you've learned anything, you should know how to verify that this is a group on your own. However, it is a group, pretty obviously so, the way we define everything, our multiplication operation and inverses and whatnot. And we showed closure, which is really the most important thing here, the least obvious of the group axioms. So I'll leave the rest for you to practice on your own, and we will move on to the next thing. Alright, so this is going to be more of an abstract video, but let's do one quick example to make sure you understand what this free group thing is. So let's pick our set X to just be A, B. And then we'll call X inverse equal to A inverse, B inverse, where we've already implicitly made a bijection here, saying this element gets mapped to that one, and that one gets mapped to that one. And then we will have, of course, our singleton, which we will still call just 1. Right? So we're going to form words on this, like A, B, B, 1, 1, 1, etc., which is going to be AA, BB, or we could just write this as A squared, B squared, right? This is a word. And in fact, it is a reduced word. Now, we want to consider multiplying two reduced words. Let's just do an example of that real quick. So how about we have A, B, A inverse times, say, A, B inverse, B. This is going to be equal to, we start by concatenating them, and then A inverse A, we're going to remove. So this is equal to A, B, B inverse, B. And then we have two inverses next to each other, so we're going to remove those. And we get equal to AB, and this is our reduced word. So the free group is just going to look like these reduced words. So you'll have, first and foremost, you'll have the elements from X. So A, B, A inverse, B inverse. You'll have those two as well. You'll have the singleton 1, the empty word, is also reduced by definition. But you'll also have things like A squared, A cubed, etc., and B squared, B cubed, etc. And you'll have things like AB, ABA, ABBA, ABBA. You'll have everything. So just everything that's reduced. I mean, you'll have A inverse, B inverse, A, B, A inverse, and so on. Just all possible combinations such that the words fit the definition of a reduced word. All right, next theorem. Let F be the free group on a set X and iota from X into F the inclusion map. If G is a group and F from X to G is a map between sets, then there exists a unique homomorphism of groups F tilde from F to G such that F tilde composed with iota is just equal to F. Now this is very similar to something we keep seeing time and time again, this universal mapping property idea. So we have a set mapping under the inclusion map to the group, the free group on that set. Then we have another map, again just a map between sets, not a homomorphism, into a group G. We're considering the group G just as a set here. And just maps between these two sets and maps between these two sets induces together a homomorphism, a group structure relationship between these two groups, which is fascinating. F tilde. So we're going to prove this. All right, so I drew our little commutative diagram over here so that you don't get too confused about what's going on. Honestly, this proof is straightforward. The only difficult part about this is keeping straight the difference between elements of X and their inclusions in, say, F, or the elements that they're mapping to in G. Just keeping those straight, recalling at all times that iota of X is not technically equal to X, but they are going to have the same name, right? It's the same element but with group structure added inside of F. So the only confusing thing really about this entire video is going to be keeping those straight, in my opinion. All right, so proof. First thing we're going to do is define F tilde for any word in F of X. Any word can be written, right, as x1 to the alpha 1 all the way up to xm to the alpha m. So we're going to define this map to be f of x1 to the alpha 1 all the way up to f of xm to the alpha m. And remember what I said about keeping these straight, right? So we're saying, let's take a word, which is in here, and it has to be able to be written in terms of elements from the set X, right? So we trace those elements back to the set X right here, and then we ask, what are those getting mapped to in G, right? So this x1 is the x1 in X, whereas this one is the x1 in F of X. And I think as soon as you see that, it's pretty obvious what's going on. We're just defining this map so that it's going to turn out to be a homomorphism, and of course it is unique, and that's what's important. So let's just go through the steps and show that this is what we think it is. So this is going to be a well-defined map because every word in F of X can be written this way by definition, and this product is going to be well-defined because G is a group, and and G is going to be closed under multiplication, and exponents, we know what those mean in groups generally, right? It's just repeated multiplication. So this is going to be a well-defined map just by inspection. We need to show that it's a homomorphism also, though. So to show that it's a homomorphism, we say for any words W1 and W2 in F of X, F tilde of W1, W2 is going to be equal to F tilde of, and then we're going to write these as we know they can be written by definition as words on elements in X, right? So x1 to the alpha 1 all the way up to xm to the alpha m times y1 to the beta 1, all the way up to y sub n to the beta n. And these represent two general words in f of x. Now for a moment we're going to concatenate but not reduce. This is just to save ourselves the trouble of going through like 5 cases here. So this is going to be equal to f tilde of x1 to the alpha 1 all the way up to xm to the alpha m, y1 to the beta 1, y sub n to the beta n. And if you want, you can reduce that. You can say, what if these two are inverses and whatnot. It's just that you're going to have to eventually restore them later, so there's no point really in reducing. And this is going to be, by our definition, equal to f of x1 to the alpha 1 all the way up to f of xm to the alpha m, f of y1 to the beta 1, and f of y n to the beta n. And this is going to be well defined in the group G. And then we're going to just group them by associativity, which we know G has associativity, so we can do that. So we can write this as this, right? Generalized associativity. And this is going to be, by this definition, f tilde of x1 to the alpha 1 all the way up to xm to the alpha m times f tilde of y1 to the beta 1 all the way up to yn to the beta n. And this is equal to, of course, f tilde of w1 times f tilde of w2. All right, now lastly, let's show that f tilde is a unique homomorphism. There's only one that has this property. Well, suppose that there's another one, which we'll call G, that goes from F to capital G, such that G is a homomorphism and G composed with iota is equal to the map F. Suppose there is a second homomorphism. Well, suppose we plug in any general word from F into G. So it looks like this. Because G is a homomorphism, recall, general property of homomorphisms is that they preserve multiplication. So we must have that this is equal to G of x1 to the alpha 1, all the way up to G of xm to the alpha m, right? Okay, now this is, because this is the x1 in F, not the x1 in the set X. This is very important, right? G is a map from F to G, not from X to G. Then this is the image under the iota mapping, the inclusion mapping, of the element x1 from the set X. So in other words, we can rewrite this as G composed with iota of x1 to the alpha 1. And we can do that for each element, since we broke it down into elements which are from X, right? Which are the inclusions of X in f of X. So we write this as the product G composed with iota, like so. And now by definition, this has to be equal to F, right? It's the unique, we're saying, we want to show uniqueness, but we're assuming that the F tilde is not the unique map such that F tilde composed with iota is equal to F, right? So this is equal to F of x1 to the alpha 1 by supposition, all the way up to F of xm to the alpha m. But this was exactly our definition for F tilde, right? This is exactly our definition of F tilde of x1 to the alpha 1 multiplied all the way up to xm to the alpha m. So we see that G actually, for every word in F, which can be written in this form, which is all of them, G must be equal to F tilde, and so we see that they are in fact the same map, and F tilde is a unique homomorphism, as we wanted to show. An important corollary. every group G is the homomorphic image of a free group. This is incredible. So why is this true? Well, let X be any set of generators of G, right? So let X generate G. And in fact, we're even going to write this differently. Let iota sub G denote the inclusion of the set X in the group G. And now we're going to have two inclusion maps going, so don't get confused by this. It's really not complicated. So we have X going to f of X and X going to G. We have iota sub f, the inclusion of X in the free group on X, and the inclusion of X and G because we obtained X as a set by taking the group generators of G, any set of them. And by our previous theorem, this must induce a homomorphism alpha, right, from F to G. But more importantly, because X generates G, or rather the inclusion under this iota sub G map of X in G generates G, then we know that each element in G can be written by definition, right? General G can be written as x1 to the alpha 1 all the way up to xm to the alpha m. These need not be countable, by the way. We could have an infinite number of generators. We can have an uncountable number of generators even. But just for illustrative purposes, I'm writing a finite word here where all these x's are in X, right? So by definition, G can be generated by that, but each element can be traced back to here and also be mapped into a word here, so that every word in f of X gets mapped to an element in G, and every element in G has an element in F mapping to it. In other words, this is not only going to be a homomorphism from F to G, but it is going to be an epimorphism. And thus, you see, just by the picture really, that every group G is the homomorphic image of a free group. So we can, in some ways, obtain every group, not even just finite groups, this is really far-reaching, but we can obtain every group via a free group on that group's generators and a homomorphism between these two. Alright, now at this point you might be wondering, if every group is the homomorphic image of a free group, is there a way to characterize all groups in terms of free groups? And the answer is a resounding yes. So we have this induced homomorphism between the free group on the generators of G and G. Now recall by the first isomorphism theorem, whenever we have a homomorphism, there is an isomorphism lurking under the hood, right? We'll have f of X, the free group on X, quotiented by the kernel of alpha, is always going to be isomorphic to the image of alpha. However, we didn't just say that alpha was a homomorphism, it's actually always an epimorphism, which means that the image of alpha is always going to be G. So there's only sort of one unknown, one degree of freedom here, and that is the kernel of our induced homomorphism, alpha. So the question this begs is, can we find, given a certain G and its generating set X, can we find a normal subgroup of the free group on X such that this quotiented by that normal subgroup is isomorphic to G? And we're going to do exactly that. To do this, we just need to recall one simple fact. If we have a family of normal subgroups indexed by some indexing set, capital I, so we'll say each of these n sub I is normal in a group G, then recall that the intersection of all of these normal subgroups is itself a normal subgroup of G. Alright, now the way we're going to do this is we're going to take some set of reduced words on X, which we're going to call Y. just some set of reduced words, not all reduced words, just any set. And we're going to consider the family of normal subgroups for which these are normal subgroups of F, the free group on X, such that Y is contained in n sub I for all I. And then we're going to take their intersection to get the normal subgroup generated by Y. So we're going to call capital N the normal subgroup generated by Y, right? Which is just the intersection of all these normal subgroups containing Y. Okay, now we're going to take the quotient, F quotient N, and if it may turn out that this is isomorphic to G. If it turns out that this is isomorphic to G, then we have found the normal subgroup we are looking for. We've chosen the right reduced words in a sense, and what we'll call X and Y a presentation of the group G, and we're going to write it like this with a line down the middle. So a presentation of the group G in terms of generators X and relations Y. Now, why are they called relations? Let me write this down. Generators and relations, and together it is presentation of the group G. Presentation. So why are the elements, clearly the elements of X are generators, but why are these called relations and why? Well, recall that what we had here before we put the N, we had F quotient the kernel of alpha, right, is isomorphic to G. And so we were looking for an appropriate kernel in a certain sense, a kernel of a certain map, such that F quotiented by the kernel, or recall that the kernel is always a normal subgroup, is isomorphic to our target here. So there's going to be a map, right? And this homomorphism is going to take elements from the free group and map it to what? Well, because they're in the kernel, it's going to go to the identity, which means these reduced words, say x, y, x inverse, right? This is an example of a reduced word, let's say, using elements x, y in capital X. Well, what's going to happen here is this is going to get mapped in G to the identity element, which is the same as simply defining this to be true in the group G. So we have a series of relations which we might call R, which are just simply reduced words on X. And these words are getting mapped to words in G, which are equal to the identity element. So we are, in a sense, when we are defining the group in terms of generators and relations, should this quotient be isomorphic to that, when we define it this way, what we are essentially doing is saying we have a certain set of generators. Let's call them x1 and x2, for example. And we're going to define it such that x1 squared is equal to the identity and x2 squared is equal to the identity. These could be our two relations. So x1 squared and x2 squared are, for instance, the elements of our set Y. Well, this is the same as just saying that we have some set of symbols, and on this set, the symbols multiply together in a certain fashion, right? There's special rules that you multiply them by. Whenever you see an x squared or an x1 squared, you know that's the identity. Whenever you see an x2 squared, that's the identity. And we can actually define a group. It should make intuitive sense that we can define a group this way. In fact, we have been sort of doing this all along. Okay, so our first example. We have a set with just one element in it, and this is going to be our only generator. And our relations Y, there's just going to be one relation as well. So we're going to have b to the m is equal to e for some positive integer m. Well, it shouldn't be too much of a stretch to be able to see that the free group on a set with just one element is going to be the infinite cyclic group generated by that one element. So you're going to have your identity, you're going to have B, you're going to have B squared, etc., and you're going to have B inverse squared, and this is going to be your free group on one symbol. It's the infinite cyclic group generated by B. That shouldn't be too much of a stretch. All right. Now, what about the normal subgroup generated by this B to the M business? In other words, what subgroup of our infinite cyclic group would be the smallest one containing the cyclic group generated by B to the M? And the answer is going to be, it's going to be B to the M. It's going to be this cyclic group, which is going to be isomorphic to M times the integers, right? So here we're going to have F quotient N. This is our N. It's isomorphic to N, rather. So F quotient N is going to be isomorphic to Z quotient MZ. And we know this as the definition of the cyclic group of order M, right? And this should make sense, right? We have one generator, and we know that that if you multiply B squared, B cubed, all the way up to B to the M minus 1, right? Our relation here says B to the M has to be the identity, so it's going to go back to the identity here at B to the M. So we have the equivalence classes of B squared, B cubed, all the way up to Bm, or Bn minus 1, and of course the equivalence class of the identity. So it is indeed Z sub M. Very familiar group by now. Okay, next example. So now we have two generators, A and B, and three relations. We have A squared is equal to the identity, B cubed is equal to the identity, and A inverse B inverse AB is equal to the identity, which if you just multiply by A and then by B on the left, you get that AB is equal to BA. In other words, whatever group has this presentation is going to be an abelian group. That's going to be important. Let's see if we can figure out what this group is, just by reasoning about it. All right, so the free group is going to have products. Let's see, well, it's going to start with the identity, and A and B. And it's also going to have things like A squared. But wait, A squared is equal to the identity, so we can cross that one off. It's going to have B squared in there. It's going to have B cubed. Well, let's wait. Let's do it by sum of powers here. So like AB is going to be another thing. And then we'll also have BA, but BA is equal to AB by this rule. Now we move on to A cubed, but A cubed is just going to be A because A squared is the identity. A squared B, this is just going to be B, right? Because A squared is the identity. So we've seen that element before. How about AB squared? This is an original element. And then B cubed, but B cubed is the identity. And so on. And I'm not going to prove this rigorously, but it shouldn't be too hard to figure out that more complicated things are going to reduce down to the elements we already have. We're not going to be able to get anything more complicated in terms of just a monomial in A and B here. And then every other element is just going to be multiplications of these monomials. And you're going to get, especially with this commutative property, more things of the form A to the K, B to the L. And so you do see that everything reduces down to these 6 elements when we quotient out, right? So what we're left with is that F quotient N, right? N is generated by y, recall, F quotient n is going to be the equivalence class of the identity, the equivalence class of A, the equivalence class of B, the equivalence class of AB, the equivalence class of B squared, and the equivalence class of AB squared. So our quotient group is going to have exactly 6 elements in it. This isn't too hard to see. Now, there aren't that many groups of order 6, and in fact, well, let's take a look. For abelian groups especially, of order 6, how many abelian groups of order 6 are there? Well, let's see, how about there's Z6, and oh, there's also Z2 cross, where I'm using cross to mean direct product here, Z3, right? This is also an abelian group of order 6. So which could it be? Well, let's see which one satisfies these properties. So Z6 is going to be 0, 1, 2, 3, 4, 5, right? Under modular arithmetic, mod 6. And Z2 cross Z3 is going to be 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2, right? Where the first coordinate is mod 2 and the second one is mod 3. So, alright, what generators could A and B possibly be? Well, let's start with Z6. For A, we need something which squares to the identity, which, because this is an abelian group, we usually talk about it as an additive group, right? So we need something which added to itself gives you the identity, and this is just going to be 3. So A is equal to 3. Now what about B? We need something which, when you cube it, or in this case when you add it to itself 3 times, you get the identity, right? Well, what satisfies that? Well, both 2 and 4 actually are going to satisfy that, right? 2 plus 2 plus 2 is 6, which is 0 mod 6. And then 4 plus 4 plus 4 is going to be 12, which is once again 0 mod 6. So we could use B equals 2 or B equals 4. Doesn't really matter. And especially because 2 and 3 and 4 and 3 are both pairs of relatively prime numbers, you're going to be able to generate the whole group using either of them. So either will work here. We never said that the generators would be unique, by the way. We just said there are 2 generators and they satisfy these relations. There may be more than one set of generators which satisfy these relations, and because of the symmetries in groups, it's often the case that there is more than one possible set here. And what about our last property, that it's commutative? Well, that's how we chose Z6, right? It's a commutative group, it's a cyclic group, so it's definitely satisfied by these 2 generators. Okay, so either of these 2 pairs would work, and it looks like this one is, it satisfies everything. What about Z2 cross Z3? This direct product over here. Well, are there any elements that square to the identity? Or rather add to the identity in this abelian additive group? Well, yeah. We have, and we're also, it's important, we can't derive just from these 2 things that A or that B is the identity element. So we can't choose the identity as a generator. That's important because it wouldn't satisfy this. You wouldn't get the same quotient. So, alright, so it looks like 1, 0 could be our A. It squares to the identity, right? Because the first coordinate is mod 2. And then 0, 1 would be a great B because the second coordinate is mod 3. So it's going to cube, or when you multiply it by 3, mod 3, it will be the identity. Okay, so we have an A and a B such that these two are satisfied, and we know that the direct product of abelian groups is an abelian group, so this is also satisfied. So it looks like this one works too. Oh, but now we have a problem, right? Which of these two abelian groups is this group presentation describing? Well, I apologize, but I've tricked you. This is a special case. It's not usually true, but Z6 and Z2 cross Z3 are actually the same group. They're isomorphic. In general, if you have, say, ZK cross ZL, it is not isomorphic to Z sub KL. That is not hardly ever true. This is just a special coincidence. But you notice how both were characterized by these generators and these relations. Next example. So, very close to the last one. Two generators, and we have a squared and b cubed as relations again. But now we left out the relation that said A inverse, B inverse, AB, right? Which we said was equivalent to saying AB is equal to BA, importantly. That was our commutativity condition. So now what happens when we leave that out? What kind of group do we get? Well, once again, we're going to have A squared as the identity, B cubed as the identity. So we're not going to see high powers of A and B in these words. However, all we need to do is construct this quick sequence. A, AB, ABA, ABAB, AB, ABA, etc. And you can see that each one of these, because we don't have any condition like this saying AB is equal to BA now, and we don't have any higher powers, we just have B's and A's separated from each other here. We see that each of these actually has to be a distinct element of our quotient group. It has to have its own equivalence class, rather. So we can draw a little equivalence class bars above it. And there's going to be more elements than just those, right? There will be, for instance, AB cubed A will have its own equivalence class, and B squared A will have its own equivalence class, and so on. But all we needed was this initial sequence to show this group is going to be infinite. It does have what I would liken to a torsion component. We haven't talked about that yet in the context of abelian groups, but so we do have some things, squaring to the identity, cubing to the identity. We have sort of a cyclic component, if you will. But even with that being the case, this is going to be an infinite group, and of course not abelian, because we need this condition, we need this relation in Y in order to show that it is abelian. So all we did was take out that one condition and we get an infinite non-abelian group, which is pretty complicated on the surface of it. Okay, now for our last example, we have two generators once again, but a new set of relations here. We have a to the fourth is going to map to the identity. We have a squared, b to the negative 2 is going to map to the identity, which is equivalent to saying a squared is b squared. And then we have b inverse is equal to the identity, or ABA is equal to b, if you want to write it that way. Can we figure out what this quotient is going to be? What this group presentation is a presentation of? Well, let's start with with all possible combinations again. Let's start with the free group and just try and reason a little bit about it. Okay, so elements of our free group. We'll start with the identity, and A and B as usual. And now we're going to have A squared, AB, B squared, A cubed, A squared B, AB squared, A B cubed. And I'm writing it in this order because I think it's the easiest to see the complexity rising in this order. So A to the fourth, A cubed B, A squared B squared, AB cubed, B to the fourth, etc. It's kind of a bad 4. Okay, now once we quotient out, what's going to happen? Well, we're going to have our equivalence class of the identity. We're going to have our equivalence class of A and an equivalence class of B. We're going to have an equivalence class of A squared, an equivalence class of A times B. And now B squared, of course, is equal to A squared, so it's going to belong to this equivalence class. A cubed is going to have its own equivalence class. A squared B is going to have its own equivalence class. AB squared is going to actually be a member of the A cubed equivalence class. B cubed is going to be the same as the A squared B equivalence class. A to the fourth is going to be a part of the identity equivalence class. And then we have, what do we have left? We have A cubed B. This is going to be the same as, I think that's its own equivalence class. Kind of cheating. Then A squared B squared is going to be in the identity equivalence class because this is the same as A to the fourth, which is the same as the identity. A times B cubed is going to be the same as A cubed B, right? So this is going to belong to that equivalence class. B to the fourth, again, is the same as A to the fourth because of this, and this is equal to the identity equivalence class. And it may not be obvious at this point. Once again, I'm not going to demonstrate it rigorously, but we have already, in fact, found every equivalence class in our quotient group. There are exactly 8 of them. So we are going to call them the identity equivalence class, A, B, A squared, AB, A cubed, A squared B, and A cubed B. So this is going to be F quotient N. So now, what group is this? Okay, I've rewritten it so we have a little bit extra space. Alright, so there are going to be 5 groups of order 8. Can you name? How many can you name at this point? We have Z8, the cyclic group of order 8. We have Z2 cross direct product with Z4. It's going to be of order 8. We have Z2 direct product Z2 direct product Z2, which is also going to be of order 8. We're going to have D4, which we have not talked about this group yet. So I'm going to slightly sweep this one under the rug. This is going to be the subject of our last video for a nice ending. So we'll leave that aside in detail, but it is of order 8. And then we have Q8, the Quaternion group, which we saw was of order 8 before. So you should have seen by now, we should have, at least in principle, seen all these groups except for maybe D4. All right, so which group is this, is the question. Well, we don't have any condition that immediately jumps out to me as saying we have an abelian group. However, these are complicated enough. Maybe you manipulate them into AB equals BA using a combination of these three relations. Maybe it's possible. I won't rule it out yet. Let's start with Z8. Now, first condition we're going to look at is that A⁴ is the identity, and because of this second condition, it's also true that B⁴ is equal to the identity. Or in this case, that in an additive group, we mean 4 times A and 4 times B are congruent to 0 mod 8. Well, the only numbers that that's going to be true for are 2, right? 2 times 4 is 8, which is 0 mod 8. 4, which is times 4 is 16, again, same thing. And 6, which times 4 is 24, which mod 8 is 0. And of course we have 0, but neither A nor B is the identity element here. So we're leaving that out. Alright, so our options are 2, 4, and 6 for A and B. But already we have a problem. And that is that no combination of 2, 4, and 6 is going to generate all of Z8, right? Because they're only even numbers. If you add even numbers to even numbers, you get more even numbers, even mod 8, because 8 is even. So we can immediately rule out that this group is Z8. So it's not going to be Z8. What about Z4 direct product with Z2, which looks like this? Well, actually we're going to be able to find elements which satisfy all these properties. But the problem with Z2 cross Z4, once again, is that it is abelian. And there is no obvious way to obtain AB is equal to BA just from those three relations. I mean, you can manipulate all day if you want, but this has more information in a certain sense than that has. So it can't actually be the same group. It has to be specified completely. They have to match each other perfectly. And in this case, the abelian nature is going to rule it out. But actually, we can find generators which satisfy these three properties, which is interesting. What about Z2 cross Z2 cross Z2? Well, once again, we're going to have the same problem as before. You really get the idea by now of how we can take elements and see if they really do satisfy these properties. But the main issue is that this is an abelian group. The direct product of abelian groups is abelian, and we do not know that this is abelian. We just simply do not have enough information to say that, so it cannot be Z2 cubed. Now, what about this mysterious group D4? Is it possible that our unknown group is this one? Well, we haven't talked about D4. I haven't even defined it for you yet, and we will again save that to next time. But I can already tell you that it won't be, and here's why. So, the only pairs of generators which satisfy A squared equals B squared are going to be R cubed, and any pairing of two of these four. So AB, AC, AD, BC, BD, and CD. So we have a bunch of possibilities here. These are going to be the only ones which satisfy, the only pairings AB, non-identity elements, and distinct, of course, which satisfy A squared is equal to B squared. And I'm just using sort of an arbitrary notation I made up for these elements, but in any case, so these are our options just from that property alone, and all of them actually satisfy this property as well. So that's a plus. But the problem we're going to find is that none of these generate the group. Not a single pair of these are actually generators of the group D4. So I know that D4 is in fact out, and it can only be one group. Alright, so our last option is the Quaternion group. Let's show that it really does satisfy these relations. So we're going to pick two generators, and the generators we're going to choose are I and J. Although we could use J and K or K and I, we can use whatever ones we want. But in this case, we're just going to choose I and J. as our A and B. And first of all, I to the fourth is what? I to the fourth is going to be I squared squared, which is going to be -1 squared, which is going to be +1. And this is our multiplicative identity. So satisfied. All right, now what about A squared equals B squared? Well, I squared is equal to J squared is equal to -1 by assumption, right? The rules we start with, right, are I squared equals J squared equals K squared equals IJK is equal to -1, right? Those are our rules for defining the Quaternion group. So, second property is satisfied. Now what about AB inverse? So, or just in this form. So I times J times I is equal to, and we're hoping to get J. So I times J is K, and K times I is what? It is J. So this is all good. So it satisfies our three properties and definitely generates the group. To get plus or minus 1, we just we multiply. To get -1, we do I squared. To get +1, we do I squared times -1, which we just obtained. I, J together can give you plus or minus K. So it does generate the whole group, and we see that F quotient N, where N is, of course, let me write it in a better way here. So F of X, the free group on X, this set of generators, quotiented by the normal subgroup generated by the relations Y, is isomorphic to Q8, the Quaternion group. All right, now an important theorem. Let X be a set, and let Y be a set of reduced words on X, and G the group given by the generators X and relations Y, defined by that presentation. If H is any group such that H is also generated by X, and H satisfies all the relations in Y, then there exists an epimorphism from G to H. So this theorem is going to give us the information we needed to talk about the intermediate case, which came up in the last example. So when we had the relations and generators as follows, this gave us the Quaternion group, right? But we said that there were several groups actually which satisfied the relations and they had generators which satisfied these three relations, but they somehow had more information coded in them. In other words, they also satisfied, for instance, the biggest problem was that they were abelian, and there was no way to tell from looking at these relations that this group need be abelian. So we had some extra relations satisfied by it, namely A inverse B inverse AB, which was not contained in Y. And this group is going to tell you what is the relationship between the group defined by these relations and the group defined by these relations plus an extra relation, right? There's going to be a homomorphism between them. All right, so proof. Let N sub I once again denote the family of normal subgroups in F containing Y. And so we're going to define capital N to be this normal subgroup of F generated by Y, which is of course just this intersection, just as before. And we're going to assume from the beginning that G is isomorphic to F quotient N, and that H is also generated by X, or rather by the inclusion of X in H. So this inclusion map, by our corollary earlier, induces an epimorphism from F to H, right? So we have an epimorphism going from F to H, which we'll call phi. We'll put phi epi. And then we have another homomorphism, namely the canonical projection map, which I believe we've talked about before, from F to F quotient N, which just of course sends every element to its coset. And then Then we're going to have an induced homomorphism. If you recall from our main theorem, as I called it, from the Isomorphism Theorem's lecture, we should have an induced homomorphism going from F quotient n to H. Of course, F quotient n is isomorphic to G, so these are essentially the same thing. Alright, so let's analyze this in a little bit more detail. Okay, so we have this epimorphism going from the free group on X into, or rather onto, the group H. Now, Y is going to be, for all words, reduced words in Y, we're going to have that phi of W is equal to the identity by assumption, right? Because we said H satisfies these relations. In other words, Y is contained in the kernel of the map phi. That's our first fact. Now the kernel of phi, we said, is always, always, always a normal subgroup of the domain of phi, which is F, right? So that means that this kernel is one of the normal subgroups n sub I, which contains Y. In other words, our normal subgroup n is going to be the intersection of all these normal subgroups of F containing Y, which is going to be, we'll say, one of these, we'll call it n sub j, is going to be equal to, the kernel of phi, right? But of course, this, the intersection of all these subgroups with the kernel of phi, has to be contained within the kernel of phi, which means that our normal subgroup n must be contained in the kernel of phi. And this is exactly the condition we needed to satisfy the, once again, main theorem is what I called it in the Isomorphism Theorem's lecture. So in other words, n is in kernel phi, so we do get the homomorphism from F quotient n to H. And in fact, we said that if the image of phi, right, this new map is phi tilde in our previous notation, if the image of phi is equal to the image of phi tilde, and it is in this case, then this implies that phi tilde is an epimorphism. And of course, because F quotient n is assumed to be isomorphic to G, then we also have, if you want, you could draw a diagram for this. So F quotient n going from phi under phi tilde to H, and then going to G via an isomorphism. There's going to be another induced map, which is going to be equivalent to phi tilde. We can call it psi, which is an epimorphism from G to H, where you simply take define psi via this isomorphism, right? I mean, it's straightforward. So we're going to have an epimorphism from G to H, and that is exactly what we were looking for. Okay, now let's talk about free products. So the free product of a family of groups is going to be another way to form a new group out of old groups. Just like the direct product or the semi-direct product, I don't know if we talked about that, we have the free product. So let's suppose we have a family indexed by this set capital I, family of groups G sub I, such that G sub I intersect G sub J is the empty set. In other words, they don't have any elements in common. And the way you can do this is just by relabeling. So if you want to take Z2 free product with Z2, you're just going to call this one, for instance, A, B, instead of 0 and 1. So we relabel them. We're making sure that they are disjoint as sets. And just as before, we're going to take some singleton whose intersection with the union of all of all of these groups G sub I is again the empty set. It's just disjoint from all of them. And we're going to form sequences once again. The words are going to look pretty much the same, except our definition for reduced words is, I mean, it's analogous but not quite the same. So we're going to have A sub I plus 1 is not in the same group. So let's say if A sub I plus 1 is in G, G sub J, say, then A sub I is not in G sub J, you know, and A sub I plus 2 is not in G sub J. So reduced is going to mean one, you know, we multiply out however many times we have to. Say you had the Z2 cross Z2 example again. Suppose we had, you know, 0 A squared B 1, 1, right? So what we're going to do is we're going to reduce this down to one element. Instead of having 0 AAB 1, 1, we're going to have whatever A squared. I guess A was our identity, so it would just be B. And then 1 plus 1, this would be 1 squared, but in additive notation, 1 plus 1 would be 0. So we'd have, this is 0, B 0. And then of course we would take out the identity, so that's the next step. The second requirement is that we don't have any identity elements in there. So A sub I is not equal to E sub J, where E sub J is, say, the identity element of the jth group. We don't have any identity elements. And the last thing is that once the 1 starts, this is going to be the same requirement as before. Once the sequence of 1 starts, it just keeps going. So we don't have any 1 sandwiched in between group elements. So A sub I equals 1 implies A sub I plus 1 is equal to 1, you know, etc. inductively if you like. Okay, so it's very much analogous to free group on a set, except now we're upping the ante. We're saying we're starting with groups instead, allowing things to get more complicated, and we're going to do it with a whole family of them. And just with these 3 rules: no group identity elements sandwiched in there, no adjacent elements of the same group, and once the 1s start, they don't stop. Those are going to be our rules for reduced words, and the reduction process is fairly obvious what you're going to be doing, right? If you have 2 inverses next to each other, once again, they're going to cancel out. You're going to remove them. If you have an identity element in there, you're going to remove it. And so we see how we're going to get the reduction process, and the multiplication process is once again just going to be concatenation of words plus the reduction. So just as before. Okay, so let G sub I denote a family of groups, and let this denote their free product. If psi sub I, going from G sub I to H for each I, is a family of homomorphisms, then there exists a unique homomorphism, psi, from the free product of the groups to the group H, such that psi composed with the inclusion map is equal to psi sub I for each I. And as sort of a corollary, the free product is unique up to isomorphism. In terms of a diagram, what this is saying is that we have a natural map which sends G1 to its inclusion in the free product, right? Because, for instance, let's say that A and B, or let's say ABC, or something like that, are the elements of G1. Well, you can consider all words on, you know, A, B, and C. You can consider all these words without anything else next to it, right? All reduced words without it being sandwiched in between in the sequence anything else. And what you're going to end up with is, once you reduce them, right, we said that we can't have adjacent elements of the same group. So this will just reduce to some element in G, whatever that is. so that we end up with a perfect copy of G1 in this free product over G sub I. So naturally we have, for each of these groups, we have the inclusion map, which takes it to its inclusion in the free product. So that's a really natural mapping. And then we also are assuming that there's a family of homomorphisms such that, let's see, we'll call this psi 1, psi 2, all the way up to psi sub n. And of course, with this n, it does not actually need to be, the free product does not need to be indexed over a finite indexing set, but just for illustrative purposes here, it's finite. So we have a series of homomorphisms here, and this is looking a lot like our normal commutative diagram, right? So we have a map going here, a homomorphism going this way, and a homomorphism going this way. And the question is, does this induce a homomorphism psi from the free product to the group H? And of course, the answer is going to be yes. I'm not going to prove this one, I'm just going to state it. It's pretty plausible. But of note is that if there's only one such map, then what we would expect is, because the inclusions are going to be the same and the homomorphisms are going to be the same each time between all the different G's and H, then if there's only a unique homomorphism from the free product to H, then we would also expect that there's only one way in which to form a free product from the groups G sub I. And this is not that difficult to see, but it is sort of a corollary of this. Next theorem, so if G and H each have more than one element, then the free product G star H is an infinite group with center the trivial subgroup. Now, first of all, with this, why are we considering them to just have more than one element? What's special about the case where they have one element? Well, if one of them has one element, then what we have is, say, G free product with the trivial group, or I should say isomorphic to. And this is just going to be all words on this identity element and elements of the group G, but we can't have elements of the group G next to each other. Recall that by our reduction rules, we can't have G1, G2 next to each other. So we're just going to have words of the form G, where G is an element of that, sandwiched in between identity elements. But once we reduce, we take out the identity elements from this trivial group, and we see that the free product is just going to be, the elements of the free product are just going to look like elements of G. So this is actually going to be isomorphic to G. So it's a boring trivial case, and so that's why we want to consider the case where we have more than one element in both groups. All right, now the proof. So for the first part, let's show that it's an infinite group. So let G be an element of G, and let H be an element of H. And obviously they're non-identity elements. Then GH to the K for just various powers of K, so we'll have GH, GH squared, GH cubed, which is the same as GH, GH, etc., is going to be reduced already. And so, with no further restrictions, we see that this free product is going to be already infinite, only considering those elements of that form. So clearly, G star H is infinite. Okay, now for part two. So let x1 all the way up to xm be an arbitrary element in the center of the free product. So recall that to be in the center, you have to commute with every other element of the group. And so what we're going to do to show that there is no non-trivial word such that it commutes with every other element is we're going to find an element which it doesn't commute with. And this is pretty straightforward. So let's choose y1 to y sub n in the group. And we're going to choose it so that y1 and xm are in different groups. In other words, if one of them is in G, the other one is in H, and vice versa. And the same thing for yn and x1. They're going to be in different groups. This is not too hard to do. Clearly such words exist. So if this hasn't, like for instance, an even number of Okay, so then if we just take the product of these two words, because we assumed that y1 and xm are in different groups, then this word must be reduced as is, so that's the answer. And then if we multiply it the other way, same thing is going to happen. We assumed that these two were also in a different group from each other, so that this word is already reduced. But now, if both of these are reduced and they're clearly not equal to each other, then these two elements do not commute. And since we did this for an arbitrary x1 to xm, it must be the case that, and I should say they only commute if one of them is the identity element. So since this is true for arbitrary x1 to xm, we conclude that the identity element is the only element in the center of the group. Center of G star H is the trivial center. Next theorem. A free group is the free product of infinite cyclic groups. So any free group can be written as up to isomorphism Z, free product with Z, free product with Z, etc. So we could write it as free product of Z, where we relabel these elements as necessary and some number of times indexed by the set I. Okay, so to prove this, proof. Let X be a set of generators. Just put let X be a set of generators, and f of X be the free group on the set X as usual. Now we're going to define a mapping psi from the free group on X to the free product of all these cyclic groups, where the generators for the cyclic groups are going to be the elements in the set X here. And the way we're going to define this map is that for any reduced word x1 to the alpha 1 all the way up to xm to the alpha m in f of X, we're going to define the output to be x1 to the alpha 1 in parentheses here, xm to the alpha m, unless we'll just say non-empty word, and it's going to get mapped to the identity in the free product if this x1 to xm is the empty word. So first order of business is going to be showing that this is a well-defined mapping. Well, showing that this is a well-defined mapping just amounts to showing that this output is always a reduced word in the free product, right? So what do we need to ensure? We need to ensure that, say, x sub I is not going to be in the cyclic group generated by x sub I plus 1, right? Because adjacent elements in words and the free product cannot be in the same original group. So, but this condition is the same as just saying essentially xi cannot be written as x sub I plus 1 to some power k. And of course, because if this were true, if it were true that that x sub I could be written as x sub I plus 1 to some power k, then this word wouldn't be reduced in the sense that the x sub I and x sub I plus 1 are distinct elements in x, right? So, because we could just write x sub I to the alpha I and times x sub I plus 1 to the alpha sub I plus 1. We could just write this as x sub I plus 1 to the k alpha I plus alpha sub I plus 1, right? Otherwise, but by the assumption that this word is already completely reduced, then we do not get this case, and x sub I is not going to be in the cyclic group generated by the adjacent element of x, adjacent in this word. Okay, so we have one condition satisfied. Now we also need that x sub I to the alpha I is not equal to e sub I. In other words, it is not equal to the identity of that group. Recall that we can't have identities of a group inside the word. And we're not going to have that either. Because the only time that this would be true would be if this power was 0. And essentially that would be removing this element from the word. And if you did this over and over and over again, what you would end up with is just the empty word, and the empty word does not even get mapped to one of the group identity elements. It gets mapped to the collective identity of the free product. So not an issue there. And the last condition is that once a sequence of ones begins, it never stops, right? Well, this isn't going to be a problem, and it's because we can't have anything sandwiched in here mapping to 1, so you can't get some output that looks like x squared 1y just by virtue of the map. The only time that your word ever gets mapped to the empty word is if the entire thing is the empty word in f of x. So that's not going to be an issue either. So these are going to be reduced, and of course these elements are going to be a member of this free product. Recall that x1 to the alpha 1 is always by definition in the cyclic group generated by x1, and for every x this is true, right? Just simply by definition of the cyclic group. So we see that it is going to be a reduced word, and it is going to be in the free product, so that this mapping is well defined. All right, so now for every reduced word, we'll just call it y1 to ym without any powers. In the free product of these cyclic groups, we're going to have, if you will, we're going to have that each y sub I is equal to x to the I to some power alpha sub I, right? This is the definition of the cyclic group. So that means that y1 to ym, the reduced word, can be written as x1 to the alpha 1 all the way up to xm to the alpha m. Of course, we have parentheses, so to speak, around these. And this has a very clear pre-image under psi, right, is equal to psi of x1 to the alpha 1 all the way up to xm to the alpha m, where again, these x1s are technically different, very subtly different from these x1s in that these are members of the free product group and these are members of this free product group. So the free group versus the free product group over here will be confusing. But this is a very clear pre-image for every such reduced word in the free product. So we see that psi is an onto mapping. All right, now suppose that for two reduced words, which we will call x1 to the alpha 1, xm to the alpha m, and y1 to the beta 1, all up to yn to the beta n, two reduced words on x, suppose we have the following, that psi of the first word is equal to the image under psi of the second word. We want to show that this is injective here. All right, well, we are going to have then that x1 to the alpha 1 all up to xm to the alpha m is equal to y1 to the beta 1 all up to yn to the beta n. And of course, because these are both reduced, we're saying that they have to be the same word. So if they are the same word, then we have m equals n, first of all, and we're going to have x sub I to the alpha I is equal to y sub I to the beta I. And have pairwise equality here. Okay, so now, because this is true, we must back in f of x have that the word x, this statement must also hold back in f of x. So we're going to have x1 to the alpha 1 all the way up to xm to the alpha m is equal to y1 to the beta 1 all the way up to y sub m, because m equals n, beta sub m. So we have that because their images are equal, we get that these two are equal. But because they're both reduced, we have to have pairwise equality. That's the only way if they're reduced. And then that means that because of this pairwise equality, that means that back in f of x in our free group, that these reduced words on x are also equal. And these were our original inputs. So we do get injectivity, right? Psi is 1 to 1. Now the last thing we want to show here is that psi is going to be operation preserving. So this is a little bit tricky, but we have psi of a reduced word is equal to, right, where this is understood to be the product in the free product group. Okay, so we have this this definition of our mapping psi, except of course when this is the empty word, it gets sent to the empty word in the free product. So because of this, all that we have to show in order to get operation preservation is actually that the rules of reducing this word, so the rules for word reduction in the free group are equivalent to the rules of word reduction in the free product group. This is going to be a little bit tricky to show rigorously, but it is going to be true, and this is what we need in order to show that psi is a homomorphism. To see that this is true, consider the following. Number 1, a sequence A1, A2, A3, let's just say so A sub n, 1, 1, 1, and so on. What is this going to get mapped to? Well, it's going to get mapped to something which looks exactly like A1, A2, A3, all the way up to AN, 1, 1, 1, etc. under psi. Now, this is not the identity operation. This is not the identity map here. A1 is going to A1, but under a new binary operation, right? And which is the binary operation of the free group, right? So pi star here. And the 1 here is the identity of the free group on x. This is identity of f of x, if you will. Whereas this one is the empty. This is the from the singleton. Recall we have union of our groups. In this case, they're cyclic groups. X of I. Union an element we call 1. Right. This is going to be the identity element in the free product. So it looks exactly the same, except we have a new binary, new group structure, and our ones have changed their meaning, but we're using the same symbol. So all I'm trying to get across here is that our map psi takes finite words, finite reduced words in f of x, and it sends them to finite reduced words in the free product. So that's our first fact. So the reduction condition in f of x, that a sub I is not equal to a sub I plus 1 inverse, is going to guarantee, once these get mapped under psi, that psi of a sub I is not in the cyclic group generated by psi of a sub I plus 1. Right? So these two are never inverses because we've reduced here. We can't reduce any further, and so we know that their cyclic groups will not intersect, right? Because a sub I and a sub I inverse or a sub I plus 1 inverse are the same thing, and this is going to be the same as a sub I plus 1, right? The infinite cyclic group generated by a sub I plus 1 and its inverse are the same thing. They're going to be the same cyclic group. But by guaranteeing that adjacent elements are not inverses in this way, we've also guaranteed that, at least so long as we relabel everything, that this image is never in the next cyclic group, the adjacent cyclic group. So we know that it is also going to guarantee that it's reduced in the free product. And the last fact we want to look at is that we defined the image of the empty word to be in the free group to be the empty word in the free product. And for any non-identity word, it is pretty obvious to see that this is not going to get mapped under psi to the identity. This is not going to happen. It can't happen by definition. It would require these exponents to be 0, which, by assuming that this is a non-identity element, we have assumed that those exponents are in fact non-zero. So we have finite words in the free group get sent to finite words in the free product. We have inverses being adjacent, being removed, is the same as reducing elements so that you do not have adjacent elements in the same group in the free product. And we have the identity here mapping to the identity, and no non-identity elements mapping to the identity. All non-identity elements map to non-identity elements. And this is really enough to see that the reduction operations, so we concatenate and reduce, right? So reducing words in the free product and reducing words in the free group on the set X are going to be totally equivalent. Okay, since reduced words in f of x are the same as reduced words in the free product, we can safely say that for all words in W1, W2 in F, that this is equal to W1, W2 concatenated and reduced. And this is why we needed this, because we need the potential reduction of this product to be the same before or after we apply the map psi, right? So we need it to be true that psi of reduced product equals reduced psi of product, right? We need this reduced part to go both ways. That's why we needed to verify that the reduction is the same in both groups, because this allows us to say that this is psi of W1 times psi of W2, and we have operation preservation. And so we have shown that this map psi is in fact a homomorphism, and not just a homomorphism, but we showed it was onto and injective as well. So psi is going to be an isomorphism, and we're going to have the free group on X is isomorphic to the free product of cyclic groups on the generators in the set X. So every free group is, in a sense, a free product of cyclic groups. Okay, so we basically reached the end for today, and next episode will be the last episode of our basic introduction to groups. However, I would like to make a few remarks before we go. So, today we saw that a free group on the set X is isomorphic to the free product of cyclic groups where this ranges over the elements of the generating set. So we see one way in which cyclic groups are useful, but we also recall that every group G is the homomorphic image of a free group on a set of the generators of G, right? Possibly in more than one way. Likely in more than one way. So this also induces a relationship between a general group G and the cyclic group of its generators, or the free product of cyclic groups of its generators, right? So we already see that cyclic groups in the free product sense are very useful in characterizing group. And we also saw earlier, when we actually talked about cyclic groups, that every group is a union of cyclic subgroups of its elements, right? So we've seen two different ways in which groups can be characterized by their cyclic subgroups. A question we will want to ask, not in this series, but perhaps in a sequel series, when we talk about free abelian groups, is perhaps there are other ways to use cyclic groups to more strongly characterize a group. So perhaps instead of using the free product, we just take the direct product of cyclic groups. What is this going to give us? What kind of groups do we get? And perhaps we don't even consider just infinite cyclic groups. Perhaps we consider a combination of cyclic groups which are both infinite and finite. And this is going to give us what are called free abelian groups, and we'll talk about this at some point in the future. The second thing I want to mention is the connection of free groups to vector spaces. Although it's not obvious now, and there are going to be several intermediate structures that are going to be really relevant for this. But we have free groups, and let's put it down here, I guess, vector spaces. You can see how it's kind of similar. Here you have a generating set X, right? So you have f of X, where here you have a similar notion, which is the spanning set, right? You could have the span of a set of vectors. And I want to draw your attention to this analogy because free groups, what we're going to do is add on several layers of structure to them, and there's going to be a path from here to here. It's going to be slow and long, and the most important thing in between them, well, there's several important things between them, right? We need to talk about free abelian groups. We also need to talk about modules, if we'll ever get to that. But I just like to think of free groups as this trailhead, which is slowly leading us toward what will eventually be vector spaces, the super high-level structure versus the super low-level structure, but that are sort of in the same direction. So I just want to pique your interest in that connection, and yeah. The last point I want to make is just that free groups were the last big puzzle piece in our basic understanding of groups. And I mean this in the sense that we started by asking where groups come from, and we never really answered that. We gave examples of groups, and I gave a motivation, but I was not able to treat that motivation rigorously. So what we're going to be doing here, very fittingly, in the end of our series next time, is to make rigorous what we did at the very, very beginning. And we want to explore the connection between symmetries and symbols. formal rules of computation. We've studied symmetries quite a bit already, actually. What with the symmetric group and cyclic groups, and really everything we've been doing has had something to do with symmetry in the background, although we haven't made it explicit just how. And then really free groups are the key to understanding this side of the duality between these two things. Groups are in the middle of these two things, and free groups explain this side. So next time we're going to see how all of this fits together and where groups really come from.